Hello everyone. Today I'll be presenting our paper that's titled Automatic Attribute Measurements of Baric Package Features in 3D X-ray Images using Deep Learning. Essentially, we want to perform AI-based automatic defect detection or 3D metrology, and that's what I'll be discussing in this paper. So the agenda for this talk would be that first I'll motivate the problem. I'll explain how we fabricate and collect the 3D data for TSVs and HPMs. Then I will go through in detail on our AI-based 3D metrology approach, which consists of 3D annotation, followed by model training for object detection and segmentation. And then I'll discuss our results and conclude this talk and give some future directions that we might work on later. So, advanced package interconnects have been getting really small as we have progressed throughout history. In 1980s, C4 soldiers were about 50 IO per millimeter square, to a point now that they are 1,000, even 2,500 IO per millimeter square, and they might even get even smaller. So the problem with this progress is that in 1980s and even 2010, the yields were really high, but with these structures getting really, really small, the yields have progressively gotten low to a point where they might not even be practical for mass production. So basically, there needs to be a paradigm shift where we can do some automated defect detection to make sure that we can go back and quickly change things for mass production. So, doing manual inspection is extremely time consuming, and as humans tend to get more careless over time, it's prone to a lot of human errors. Hence, there is a need for AI-based automation. Now, AI-based automation requires various different steps. Uh, Such as first you need to fabricate the data, then you need to perform data collection, followed by manual data annotation, and then comes the major software side AI component, which is model training. You perform data analysis, sometimes called post-processing or 3D metrology, and then you need to look at some recipe optimizations where how do you basically go back and correct these issues that we are facing when we look at the data, and then what parameters do we need to put in the tools to fabricate the required data. And then the cycle can repeat multiple times before we basically finally arrive at a really good solution. So in this work, we basically focus on two different structures, TSVs and HPMs. For HPMs, we're looking at logic die and memory die. Uh, and the 2.5D systems in package basically consist of multiple devices and packages assembled on a TSV interposer. The silicon chips with copper pillar interconnects are stacked to fabricate these HBM packages. And these packages are very critical for 2.5D systems and package reliability. Um, the the flow through for the fabrication of TSV and HBMs is provided here and discussed more in detail in our paper. So once we have fabricated the data, the next step is how to measure it. And essentially for that, we use a commercial 3D XRM machine tool called XRM Versa to obtain our data in 3D voxelized format. Specialized 3D analytics software tool is used for this particular work. And what this tool also performs is basically it can overlay the 2D virtual slices onto 3D volumes. It can also help us automate the process of identifying and annotating the TSV and HBM structures. And also at the end, once we have integrated our solution into it, we can also display important characteristics such as bond line thickness, display defects such as voids, pad misalignment, etc. So automated 3D metrology, the AI package as a whole requires multiple steps. First of all, given the data that you have fabricated and measured using the XRM tool, you need to annotate the data in 2D or 3D. After that, we need to process the data. This can be a pre-processing step where we clean up the data, or we identify the data that we need to use in our AI models. After that, we'll train our models for 3D object detection to identify the major regions in these chips that we'll be looking at for cropping as well as pre-processing before it is fed into our 2D to 3D segmentation models. The segmentation models are very expensive computationally, and hence you cannot feed the entire 3D voxelized data into it. That's why there's a need for object detection before we can feed it into segmentation component. And once the segmentation is done, we can do post-processing followed by 3D metrology, where we can measure the defects. We can talk about um, solder extrusion. We can talk about bad misalignment, or how many voids we found in a structure, what is the volume of the voids, and so on. So for our work, we basically collected data for TSVs, logic die, and memory die. While we have a lot of unannotated data, annotation is an expensive process. It takes time. Hence, for TSVs, total we annotated 277 TSVs, out of which 221 was used for train and the remaining for testing. For logic die, we had about 1,000 for training and 170 for testing, and memory die about 1,700 for training and testing about 300, summing up to 2,000. The reason why we don't have anything in validation is because some models like SST do not use a validation set. So to be on parity, we basically split the data equally. Annotating the data for segmentation is a lot more expensive because you literally have to go down to each voxel and look at it and see whether which class it belongs to, such as your copper pillar, solders, and so on. Hence, we have a limited TSV, limited asset for segmentation. For TSV, we had total 13 annotations. For logic die and memory die, 30, equally split between void and non-void. So about 15 of them were void logic die, and 15 memory die contained voids as well. So now I'll explain a bit more on the our approach for object detection and segmentation. So what 3D object detection essentially means is, given our voxelized data, we want to identify 3D bounding boxes for each different structure that's present in it, whether it be TSV, logic die, or memory die. And essentially we can draw bounding boxes around these and then use these bounding boxes to crop the data to come up with these smaller voxelized regions that can be fed into our segmentation model. There are various ways to do it. You can do it in 2D, you can do it in 3D. We started with 3D detection directly. However, it's very computationally expensive, and our 2D models were giving us great results. So in lieu of that, we basically stuck with our hybrid 2D solution. For 2D, we tried both SST, which is single shot detector, and YOLO V4. YOLO stands for you only look once. YOLO V4 basically has been working great for us, and hands down gives us the best results in terms of object detection. Our solution essentially is our solution essentially is to basically combine the results in 2D and then collate them to get results in 3D for each slice. For 3D segmentation, we looked at we are looking at volumetric data over here. So essentially the voxelized data that you see are essentially layers of 2D scans. So essentially segmentation is like a classification problem. Like you see data sets between cats and dogs, you are classifying each image into whether it's a cat or a dog. In terms of segmentation, for each voxel, or in 2D, each pixel, you are essentially classifying it to whether it belongs to a cat or a dog. So in similar sense, so this makes it very, very expensive because you literally have to go down to each voxel to do it. And doing that for the full data would be very expensive, right? Because each of these voxelized scans is 1,000 by 1,000 by 1,000, which is 1 billion voxels. Hence the need for doing object detection and then doing segmentation. So for segmentation, essentially we go from 2D to 3D in this work. In 2D segmentation, people will generally use 2D CNNs. In our case, we use 3D CNNs. And however, one drawback of using 3D CNNs would be that sometimes it's difficult to detect these small defects because they occupy a very small percentage volume. So for 3D segmentation model, we basically have three different approaches. We tried VNet, we tried NN unit, and we tried anisotropic network. That is our progress from previous papers. So VNet is essentially like a 3D unit, which works really well for 3D data. Essentially, it adds one more dimension on top of what 2D unit already did, along with all the tips and tricks that people have discovered over time to improve the baseline 2D networks. So it consists of encoder, decoder, bridge, and shortcut connections. So for each encoder, basically each layer consists of two 3x3x3 convolutions, followed by a batch normalization and ReLU, and then a 2x2x2 max pooling with strides of 2 in each dimension. For decoder, where we are basically sampling, each layer consists of an up convolution of 2x2x2 of strides of 2 in each dimension, followed by two 3x3x3 convolutions, followed by again a batch normalization and ReLU. And for essentially for your shortcut connections, this is needed so as to provide equal resolution in encoder path to get basically high resolution features for the decoder. In the last layer, we basically have a 1x1x1 convolution to reduce the number of output channels based on the number of labels we need. So if we are doing binary segmentation, we'll only have two labels. If we're doing multi-class, we'll have multiple labels. So for TSVs, where we're looking at solder and void, we have three classes, one for background. For logic die, on addition of solder and void, we also have copper pillar, hence 4 classes. And for memory die, we have basically the background, solder, copper pillar, void, as well as copper pad, and hence need for 5 classes. NN unit, so NN unit stands for no new unit. Again, if you look at it, VNet basically developed 2D unit into a 3D unit along with all the tips and tricks. NN unit basically says that we already have a very good 3D unit or variants of 3D units. What we want to do is not come up with a new architecture. However, what we can do with this architecture, what fine tuning we can do to get the best results as possible. So they essentially focus a lot on pre-processing. How do you crop the data? How do you resample, normalize? They use 5-fold cross-validation and use cross-entropy and dice loss. And for augmentation, they basically have certain pre-selected augs that work really well for the given data set. So for each data set, this augmentation may vary. And for post-processing, they use connected components if they're using also, especially if they're using 2D segmentation followed by post-processing to convert that into 3D. And they have 2 or 3 different networks that they basically internally the model will try and see whether combining results on these networks gives them better results or not. So and the third network we tried is essentially anisotropic convolution neural network. The patch size we use is 19 by 128 by 128. Essentially, the network involves 10 residual blocks with anisotropic convolution, dilated convolution, and multi-skill prediction. You can look at our paper for more details over here that I'm skipping here in view of time constraints. So essentially, this network learns local and low-level features in shallow layers, and then global and high-level features in the deeper layers. And there are 3 regions of interest for the 3 different views, the axial, sagittal, and coronal views that we basically refer to them as the 3 different planes, especially if you look at biomedical data. And then we train an anisotropic CNN model for each of these 3 different views, and then we basically combine the results from all 3 of them using die-score to basically then classify for each voxel which class it belongs. So for our data set, we basically use the standard train while test split protocols. Essentially, majority of the data is in train, and then we also use a validation data set to tune the hyperparameters. And then there's a test set as well, which is never ever seen by our training or by our model for training or validation. Hence, this gives us an unbiased estimator of how good our model is. For augmentations, we basically use elastic deformations, we use rotations for all 3 dimensions, and we use scaling as part of our augmentation module. So before I go into details on our results, I just want to explain two concepts that we'll look at in the results. The first one is intersection over union. As the name suggests, the formula itself basically says intersection of the ground truth and the prediction divided by the union of ground truth and prediction. So if our ground truth is really, really bad, then our intersection will be close to zero. Right, and our IE will be almost zero. If our ground truth and our prediction are almost similar, then this value will be equal to 1. This type of metric is usually used as a loss function as well as a metric for bounding boxes or for object detection. On the other hand, dice score or dice coefficient essentially is 2 times the intersection divided by the sum of the two predictions. And this is usually used for segmentation networks. And there is, as you can see, they're quite similar. And there is actually a correlation between dice score and IOU. And in fact, if you know the dice score, you can calculate the IOU and vice versa. Usually speaking, dice score is widely used for 3D segmentation for a variety of reasons, while IOU is more commonly used for object detection. Okay, so now that we know the important concepts, we know what we are looking at, let's look at the results now. So for object detection, we basically use SST and YOLO on the three different structures, TSV, logic die, and memory die. As you can see, the YOLO basically gives us the best results. For 2D, the average precision is 0.998, 0.997, 0.993, which is almost close to perfect results of 1. And for 3, and we were able to detect every structure in 3D. So over here, we actually show you the IOU to show you how good the results were based on our module that contains some structure recovery along with the baseline YOLO V4 module. Okay, and so for TSV, for segmentation, basically now we present the results individually for all these three structures. What we have found so far is that we basically perform two types of experiments. One where we do not augment the data at all. We just basically use the limited data that we have annotated, and then run our models of VNet, NN unit, and chi-CNN, and we also augment the data, and then we look at the results. So overall, you will see that basically NN unit performs exceptionally well compared to VNet and chi-CNN for TSV data. And usually what we have observed is for reasons, our results for especially for anisotropic CNN decrease as we augment the data, which usually is not the case. For logic die, we basically have similar observations, and the unit performs really well, while VNet comes close enough. However, for anisotropic networks, basically the results drop with augmentation, and hence there's a big delta between NN unit and chi-CNN results. For memory die, where we have basically 4 different structures to look at: copper pillar, copper pair, solder, and voids. You can see that over here, VNet sometimes can take over and even beat NN unit, while sometimes, in fact, our anisotropic CNN network does really, really well compared to the other two networks. And we see similar observations after augmentation for VNet and NN unit. However, as I mentioned, for NCI-CNN, the results tend to drop after augmentation. That's why you don't see NCI-CNN beating anyone during the after augmentations. So in conclusion, we have presented our approach on automated 3D metrology for various test vehicles replicating 2.5D and HPM construction. We also demonstrated the fabrication steps that are needed, for these different structures with the various 3D XRM tools we use for measurement. How we do the object annotation, and then what models we use for our deep learning based approach for object detection and segmentation, and then we showed our results for detection, segmentation, and metrology. The results are very encouraging with definitely scope for improvements. The results will improve once we have more data or once we are able to refine some of the kinks in these models. there needs to be a bit more effort put in future for exploring the best model. Perhaps rather than using NUnit for everything or VNet for everything or NKCNN for everything, I think the best results would be a mix and match of what works best for a particular structure for a particular component. So in future direction, we want to look at exploring the right augmentations, because the augmentations we have currently we can see that they don't work really well. We can perhaps also look at generating some synthetic data set to improve the results further. We can look at anomaly detection and semi-supervised learning as our future directions. Thank you so much for attending this talk. If you have any questions, please feel free to email me at this address. Thank you.